experiments themselves. But notwithstanding, they've been put in a way, or hopefully explained in a way, that even without that, you can still make logical conclusions or deductions and be able to generate some sort of report based on what you've read or evaluated. So let me talk through exactly what that report would then constitute based on that. Again, you are required to present a cover page, which you realize you are judged on only because at the end of the day, once you're submitting any type of document, you have to have that cover page, which provides basic information about the author as well as what is contained within the report. So you are judged, and if you realize the mark associated with it is ridiculously high compared to the total mark. If something is worth 20 marks, you get one entire mark just for putting your name. And that's because it is critical at the end of the day. If it's not there, the report has no substance, right? Secondly, you have the introduction. And I tell you, this introduction should present enough background. Now, here's the problem. Your assumption about what background constitutes is probably where the issue is, right? So some of you spend time defining each and every term, right? Rather than just explaining in general, because once you do a general explanation, the term definition will be included in it. So you don't even have to, after you've gone ahead and defined a wave and talk about the fact that there are transverse versus longitudinal waves, your definition should end right about there. There should be no reason for you to do any more definition. And even those you don't need to define, because you can easily explain them, where you say waves transport energy, and of them, there are those that cause the oscillation in one direct, what is it? Not perpendicular to the direction of motion, where those that cause oscillation. And then in brackets, you would have put the transverse beside those that are perpendicular, and those that cause oscillation in the direction of motion. And in brackets, you would have put longitudinal. That's one sentence. Whereas you would have otherwise spent time not only defining each and going through, but you would have had 4 or 5 sentences just for the one sentence right there. And then you go and you are using verbatim information and also failing to put them in quotation marks and then citing them properly. So then and again, you have those issues, and then you spend time not only thereafter going through all the different definitions. That's a waste of time. Your purpose for your introduction is just to provide enough background. In other words, explain the concept as a whole, right? If there's one term that you think that the individual may not be versed with, then certainly you can go ahead and define it. But your purpose should be to explain it, right? Explain the concept. So now you're talking about Young's modulus. Well, what on this planet is Young's modulus? You're going to have to explain and bring enough information, because then if you define Young's modulus and say it's the ratio of stress to strain, that's no explanation, right? That's a definition, yes, or that's how it's calculated, yes. But you haven't told me what information does it present. Well, Young's modulus tells you how much force that you would need to apply to a material to cause a certain amount of extension, or how much force you'd have to apply to a material over a given cross-sectional area for that particular material that will cause a certain amount of extension. That's what Young's modulus tells you, right? But I have not defined it. I simply explained it. So then you will have an idea, therefore, that if you need more force to cause an amount of extension, that means the Young's modulus value will be larger, without me even having to tell you that in words. So your background is an explanation. It's not a definition per se, unless you find a way to use the definition as an explanation, right? And then you tell your aim. You say exactly what you're going to do. If it is that you are going to determine the Young's modulus of the Y, that's what you say. But if it is that you're going to determine if the experiment is suitable to allow you to determine the Young's modulus, that's exactly what you say. And so your conclusion must answer the aim. But before I go to the conclusion, so that's your introduction, explaining, giving enough background so that the individual understands the concept that you're going to explore in detail, right? And then you say what you're going to do. Then you have your apparatus. You do not list them. You simply refer to the source. Perk up yourself, Mr. Swaby. Hands off the face. So then you also have your method that you're, instead of you stating how you did it, right? You simply refer to the source because it's already there. Now the results part, and I'm hurrying up so I can get to the discussion because that's the important part too. The results part, this is where you present all of your information, all the tabulated data, the non-tabulated data, your graphs, your calculations. Some of you will notice that I give you formatting, I give you a -1 for it. That's because of the simple fact that I gave you a specific format that you are to maintain in completing our reports. Why? Every single solitary organization, every journal, everybody, that institution that exists has a particular format for the way they want their reports done. They may be similar to each other, they may even be completely different. However, once they are going to be collecting reports from you, they want it in that particular format. And if you are not at a stage where you are able to follow the required format, then your reports or your information will be benched, full stop. It will get nowhere. So as a result, you lose marks if you do not follow the particular format that I've given you. In other places, it's not a matter of losing marks. They don't even accept it. It gets returned to you. It's rejected, literally. So if they say to you they want full stops at the end of the intro, when you write the word introduction, they want a full stop there and you don't put it there, they don't even to see if what you have makes sense. It gets sent back to you as rejected. So it is important for you to be able to follow formats. The next thing is with your results now, you are told tables must have titles, titles go above. Figures have titles, titles go below the figures. You're also told to present your information in a consistent, logical manner. The first thing you had to do was get some information. Those are what you tabulated. Then you perform some sort of some task. You executed something on them, right? Those are where you start to present whatever calculations you did in order to know further, get some more information, the relationship, which is what you present in your graphs. And then after you've drawn the graph, you also do further calculations to get your final result, your final data. And so you present it in that logical manner. You've got your table that presented the data in the first place. Then you did some calculations on them that you allowed you to complete the table. You show that. Then you also drew your graph or created or generated a graph so that you could show a relationship. You present that, and then you also had to do further calculation. You then present that. So this that I'm saying, I've said to you enough times too, and they're also in the comments. For information that cannot be tabulated, and I've told you this from the very first session, data which you collect, which are 3 data points or less, you don't tabulate them. And if it is that the data are not interrelated, you do not include them in the table. You only include those that are interrelated, that you can show that for this column, all of these values, despite the fact that they're for different quantities or for different measurements, they're all related in this row, right? So if they're not interrelated, they don't get tabulated in the same table. Then, in terms of your how you write your results, I've already told you need to define your terms, and I show you how to define them. The very first time I showed you how to define them, I did not evaluate or grade you on that. Thereafter, though, I evaluated you and graded you based on how you define your terms. If you remember to present your units every step of the way, and for instance, like with Young's modulus, and I will show you, if you do not carry your units, you're going to make a mistake and you will be off by orders of as much as 10 to the 6th, right? So as a result, units are important every step of the way, and this is why I take off marks, and I've told you this from the very first day we worked together. Now, moving on to the discussion. This part is where you are now going to explain all of your results. So I see where some of you go through the step of defining terms again. So you say, well, Young's modulus is this and that, and you go through all of that. That is you repeating background. That should have been in your introduction, if anywhere. Your discussion is solely for the purpose of explaining your result. I've seen where some of you, even though I've told you, listen, it's just to explain your expectations, some of you still go back and say, listen, we collected, we got the data, we completed a table, we then did some calculations, we generated a graph, and on the graph we got the gradient, and after we got the gradient, we got this value for the gradient, and we used it to calculate XYZ. That is you repeating the method of conducting generating your results, right? So even if you're not repeating the method of conducting the experiment itself, you're repeating the method of how you generated the results, which you don't need to, because clearly if you've presented your results in a chronological manner, an individual can see exactly what you did and how you got it, right? What you should be doing is explaining your expectations, why, if you got what you were expecting to observe, and explain why you got what you observed. And if it is that you didn't get it, you suggest.
For the introduction, just to ask you, could you state what you expect from the introduction also?
Oh, repeat the question, Mr. Hodges. I don't think I understood.
I'm saying from the introduction, can we put what we expect in the introduction in itself or no?
Well, when you're doing the introduction, really is to introduce the topic, right? So if it is that what you're expecting, you think is background information, then certainly. So suppose, for instance, you have determined that for the Young's modulus there should be a proportionality between the stress and strain, then, right? Then you think that is something important for the individual to understand before they get into it. Then certainly you would say in your introduction, you explain what Young's modulus is, you explain the concept of stress and strain and what information they provide, and then you can go ahead and say that generally it has been shown in the past, or it is right, it has been shown in the past that there is a proportionality between these two, and that proportionality is guided by Young's modulus, right? And so therefore, in this experiment, we intend to demonstrate that there is that proportionality, and by calculating the Young's modulus for a test while. So certainly. Okay. So for the discussion again, right? You don't need to really write the words we expected, but you can go ahead and say that generally this should happen, and this is what happened, and this is and the reason why. And then when you're saying the reason why, you have theories that guided that was why it is possible in the first place. So you refer to the theories. There are equations that make it that allowed you to generate the relationship and show it, because that's what you were trying to prove. So you present your equations. However, if you're presenting equations in your discussion, you have to define them. If you hadn't, as you should have, defined them well in your results section, then you would have simply referred to the results section wherever they were previously defined. So you would have said, as defined, so you write the equation as governed by this equation, wherein the terms are previously or are defined in the results section. And you don't have to redefine them. The individual knows to go to the results section to know what each term represents, or you can simply redefine them at that point in time, right? But somehow you have to define them or refer to the definition for them, right? For the symbols. So that being said, if you expect an exponential relationship, you simply you go ahead and describe that as seen in figure 1, there is an exponential relationship between, and this is not the case for stress and strain, but I'm just using it, between stress and strain. And this is because of the fact that according to the theory of whatever, there should be, as the force increases, it should cause deformation, and this deformation is squared, and as a result, it causes whatever, as can also be demonstrated in the equation, wherein, and you go ahead and explain, right? If it was that it was a proportionality, again, you go through the same process of using the different theories and the different equations, which I'm sure you've heard me say a number of times, right? But you see, when you start to question things, then when the explanation is repeated, it actually resonates at that point in time, right? With the in terms of when you don't have your expectations met, then clearly you have limitations, and sometimes the limitations are even though the general expectation was met, so you generally saw a proportionality. However, based on the fact that you had a wide uncertainty, or when you looked at the graph, the points were so far off from the line of it, which indicated that there was a substantial amount of uncertainty, then clearly you have limitations that you need to know, explore, and explain. Now you can't write it to the fact that we had this as a limitation, right? You can only suggest what may have been the limitation in the carrying out of the particular exercise. Why? Because you didn't complete it yourself. So you can only suggest. So you can say it is supposed, or it is possible, or it is probable that this was caused the problem. Now you do not write that there were systematic errors and human errors as well as environmental conditions. You have to be specific. That's what the purpose of you generating the report for this particular exercise. It's not a general report you're generating. It's a particular set of data that you evaluated that you need to report on. So therefore, your limitations must be specific to it. So you can suggest that if, for instance, they're evaluating Young's modulus, I'm going to tell you, of course, that the cross-sectional area is going to be assumed constant. You can then suggest that that assumption may not have been so. It may have been that the cross-sectional area changed as masses were included. And as a result, this was not captured in the data collection or in the data calculation, which then would have led to some amount of uncertainty. You notice that that problem of the cross-sectional area changing is a type of systematic error, but I didn't classify it as that. You know what systematic errors mean. So does the individual who is reading the report. And so as a result, he or she or me will be able to, once you've explained what the type of error is, will automatically classify it as a human or a systematic or whatever type of error. So there's no need for you to say it, because you are showing that you know what the error. 1 second, please. Let me let in this gentleman. Right, sorry about that. So you are showing your understanding of the concept plus your application of it. So you've gone past understanding. Understanding is when you simply You say yes, there are systematic errors and which are subject and you potentially subject. But once it is that you're stating it for your specific situation, you are at the stage of application, right? Application of knowledge. So the conclusion thereafter, if it is that you're doing a large study, then you would have many conclusions. So your conclusions would be paragraphs, 2, 3 paragraphs. You are doing a simple experiment, so you only have a one sentence, two sentences is the most conclusion. It must answer the aim. It must confirm it, verify it, answer it every size and herbs and answers for the aim. So if your aim was to determine Young's modulus for a particular wire, your conclusion says the Young's modulus for the test wire was found to be. You do not say it was that because you do not know conclusively that that value that you got was correct or accurate. You can only say what you found it to be or what you got it to be. So you stated. If your aim was to determine if the method was suitable to determine the Young's modulus, and thereafter use it to calculate it, then your conclusion will be not simply that the Young's modulus was X, but that the method was found to be a suitable means of it because it allowed for the calculation of the Young's modulus, which was found to be, and you provide it and full stop. So your conclusion is something that once someone reads your discussion would have come to that same conclusion themselves, because in your discussion you would have explained why you got that proportionality and why you were able to then generate the Young's modulus from it, and then they would have been able to say yes, the method was good based on what you explained. If it is that your decision was that the method was not good, then your conclusion would be no, this method was not appropriate because we were not able to find an accurate Young's modulus for the test wire, and that's if you would have known what the true value would have been. And in that case, individual, based on all the limitations that you explained, based on the fact that there was no proportionality found, even though there should have been, based on everything that you explained, would have drawn that same conclusion. So you see, your discussion really is for you to explain what you expected and why you got what you got, or why you didn't get what you should have gotten. Go ahead, Mr. Hardy.
So you know something was something.
Because I could see it in your face.
Yeah. Alright, miss. You're alone and clear when it relates to what you should expect or we should get. So I'm gonna try put in all of that and see what bears it. Just a question as it relates to the previous lab though. It was on my mind. To the diffraction grating lab that we did last week.
Mm-hmm.
For the graphs, I'm seeing where some of our graphs, well, my graph had a curve, was curved. So I was wondering by doing, and I got the line of best fit and whatnot, and I did the method of the gradient of y over x. Was that the correct method of finding the gradient for the diffraction grating graph?
You had a curve. So
It had a curve, but I'm not sure if it. Yeah, I'm not sure. I know that for a curve, it's supposed to be the tangent of 1 point or something like that. But
So you did sine the angle, right? You didn't just draw the angle versus the wavelength. You signed the angle and then drew that versus the wavelength.
Right, miss. It came
curve.
Right. I find right, and it seems curvish, miss. So I wonder what was that. I don't know if I don't get some curve type thingy, but I signed the angle and everything like that.
Okay. Well, and for those that I had looked at, I didn't see a curve. Not from what was submitted from those when during our time together last week. I didn't see a curve, but I would have to see. So usually, though, when you have a curve, you can't get a gradient for a curve. You can get a gradient at a point a gradient for a line at a point, right, along the curve, and that line is the tangent. So you can draw a tangent line at a point and get the gradient for the tangent line, but you can't generally get a line of it. What you can do if the data is really um, it's still a proportionality, but it just has a slight curve. You can do a regressional line, or you can call it a line of fit, same way, right? A proportional line of fit, but it's a regressional line. It just shows the general trend in it, and then you can do a gradient for that regressional line, right? Which it sounds like is what you did. So
Okay.
you distributed, even though you saw a curve, you drew a line that distributed the data points evenly on either side. The
Right.
distance of each point had representation on either side. So if
Right.
it was far, you had on the upper side, you had a far one on the underside, and those sort of stuff.
Right.
That's you do showing the trend and doing a regression line, and then you can get a gradient from that. So that's that's fine. I look at it carefully.
All right. But don't make me a target, you know, miss. Just meant.
Oh, I target no one.
All right.
Okay, sir. And then so in terms of your graphs, so please don't forget, remove your, but if in the initial stage, remember you would have maintained that. And so once I started telling you to remove it, that's when I would have started evaluating you on whether it's there or not. So in the initial stages, it was there only because you needed it, right? So it's transition, you're transitioning. Right now you're at a stage where your report should be presentable in a format that any you carry to a journal, you carry to an organization, they can accept it. The very first few that you did, it wouldn't have had that nice layout and that nice format because you were using the grid lines to allow you to determine whether the data points were within one subdivision away. They allowed you to be able to align and determine where you want to use, which points you want to use for your gradient calculation. So they were necessary for you in the early stages as you were learning how to generate the graph and to use it. Right? So now you're at the stage where you're simply presenting information. You no longer need grid lines. You are able to quickly look at it and know whether the points all fall within one subdivision away. So even though, Mr. Hodges, you think that you are not transitioned because your grades stay the same, that's only because the evaluating, what you're being evaluating on is also changing as you increase or improve where you are. And if you notice, I'm sure you're faster at generating a report now. You're also fast at evaluating the information and figuring out what it is that you need to start looking for, even though you think it doesn't align with what I am asking. You are better able to do so. You are better able to discuss now. You are the information on how you lay it out is far more improved, and even in terms of how you present your graphs, your tables, all of those things, how you do your calculations, the type of calculations, the method, you are better at it than your first school. So, thumbs down, you don't agree? There we go. All right. Any questions, Mr. Swaby?
No, Miss.
Okay. Okay. Miss Saman, any questions?
No, miss.
Just sure about this.
So, miss for the calculation thing, you're marking for equation, right, miss?
I mark for how you present your information, yes. And I mark whether it is that I know what the term means or not. Which means that if I don't know what it means, you haven't defined it.
Alright, some people have some old laptop in them, so the new one then they can insert some old laptop, miss. The new one then they can insert equation in it, but the old one then they cannot. And if you
Almost.
do it old fashioned way and put flash division, there's nothing wrong with that.
No, absolutely nothing is wrong with that. And certainly you notice some persons use the what you call it, the insert bar and to indicate that the term of the number afterwards is going to be superscripted. Although all computers can allow superscript these days, but it's there and it is unacceptable. However, you don't want to keep using that method when you can use the more improved. So there are persons don't all write equations because some come and I don't mark it down for the fact that you haven't written it using equation editor. It's a matter of how you write it. For instance, if you have 5 minus 2 and you want to write seconds, but you put the seconds on the end, but 5 should have seconds too and 2 should have seconds too. You either should have written 5 seconds minus 2 seconds, or you write in brackets 5 minus 2 and then put the seconds on the end. Right? So that is different. So I do mark for how you present the information because three things are different. 5 minus 2 seconds cannot be done because 5, you can't subtract different quantities from each other, and 5 is not a quantity because it has no unit. And so when you have 5 minus 2 seconds, that's totally different from 5 seconds minus 2 seconds, which is again different from 5 minus 2 in brackets or seconds. Okay. All right. So it looks like we went way over in that, but hopefully we're more clear. And I will remind you, because I realize I do have to do so, that basically what I just went through, I've been saying it all along. It's just that it's now resonating. I guess now you realize the impact it has on the grade. Right? Which is on. Yes, Mr. Hodges, I see you shaking your head, but yes, it's true, is that. Okay, so I'm going to go ahead and share the screen and talk about today's experiment or exercise. Let me increase the grid so I can still see you as I'm sharing the screen. And I don't know why I'm still not seeing everybody. Mr. Brown, you can close the camera screen, I can see that you closed it. The screen over your camera. All right. So, young modelers, are you
Miss, give me like
I didn't hear Mr. Blake. Okay. All right, so young modelers, right? So, you would have learned that Young's modulus shows the relationship between stress and strain, but then Mr. Simpson would have also explained to you what stress is versus what strain is, right? So here's what happened. Once it is that you apply a force to an object and you do it in the one dimension, right? So we're not talking a two-dimensional force being applied or even a three-dimensional application of the force. We're talking along one dimension. So once you apply a force along one dimension, generally to an object, you can cause deformation of this object. You can cause it to either compress or elongate, depending on the type of force. If it's a compressional force, you can cause it to get smaller, contract, compress. Or if it is a tensile type of force, a positive tensile force, you can cause elongation, cause stretching, right? This generally happens for almost everything. Even as you're standing up in the building, even as you're sitting in the chair, even as your feet rest on the floor of the below you, you're applying forces to be, and it is causing some amount of compression. However, it's not observable, or the compression is so small that you can consider it to be negligible. It's not immediately something that is going to show or demonstrate, which is why engineers, as they're designing buildings, as they're determining the strength of the concrete mix, even contractors, as they're determining whether to put in posts, whether beams, or posts, depending, because remember, posts are the vertical versions and beams are the horizontal version. As they're trying to determine whether to put these in or not, they have to consider some of the forces that will be applied to the structure, and these forces will cause compression or even extension, right? And they have to put in the structures that will facilitate the different types of the different amounts of compression or elongation that may occur to the building. It's the same concept irrespective to, even with you will have learned about shear forces, shear modulus. As in designing the car, they have to consider the shape, so that as the force of the wind, the resistive force of the wind hits on the vehicle, it can cause the force. You would have heard of it as aerodynamics, but it will also cause shearing along the different layers of the vehicle, and the vehicle has to be able to withstand all of that, right? So these concepts tell you, for the particular material that you use, the whole thing of Young's modulus or shear modulus tells you how much force can be applied before you get a certain amount of extension, elongation, a certain amount of shearing. Oh, this is absolutely strange. Mr. Morgan, beyond this, where's the pen? Right? Sorry about that. Mr. Morgan, you're extremely late. You're an hour late. You're lucky today.
I am very sorry, Mr. I apologize for being this late.
All right, Mr. Morgan, it's your lucky day. Consider it so. All right. So that's what those concepts tell you, right? So you can then imagine that the larger the Young's modulus is, the greater amount of force that can be applied before it will have any stretch by about a meter or so across a particular cross-sectional area of the object, right? So you now are going to explore this concept in this exercise. So the relationship now, as I mentioned to you, you can, instead of looking at it as simply force causing an extension, you can also look at it in terms of stress versus strain. Now, stress is the amount of force that you would apply across a particular cross-sectional area, and that's a concept of pressure. So as a result, it has units of Pascal. Strain now is how much you can extend the object by per meter of the object, how much extension can be garnered or achieved per meter of the particular object that you're seeking to apply your compressional or extension force to. So that relationship is going to be guided by the Young's modulus, which tells you is the stress divided by the strain, is the ratio of the stress to the strain. It is the amount of pressure that you can apply that will cause a certain amount of compression per unit length, right? The amount of force that you can apply over a cross-sectional area that can cause an amount of extension per meter of a device, of an object, right? The larger the Young's modulus is, the larger the amount of force that you can apply that will cause a certain amount of extension per meter. The smaller the Young's modulus is, the smaller the force that you can apply to cause that particular amount of extension per meter. Right? So that's what Young's modulus tells you. So you are going to be trying to see if you can determine the Young's modulus for a particular wire, a test wire. And so that's what we're going to go ahead. So this is how the setup would be, right? Let's put it down. This is the apparatus set up for the Young's modulus experiment. In this case, you have two wires, right? They are both of the same material. They are both of the same initial length, right? So one of them serves as the test wire. That's the one that you will be applying the force to. Now, how you apply the force in this particular exercise is you will apply masses to the wire. And because you're applying the masses without having any sort of support beneath them, then these masses will feel the force of gravity acting on them, which they will transfer to the wire as a tension force. right? And this tensile force will cause some amount of extension of the wire. So, therefore, the force value or the tension value in the wire will be the weight of the masses that you've applied. So you will apply a mass to the test wire, right? And it will cause an extension. The comparison wire is there, right? It would have been at its original length. So you would have taken note, this Vernier scale is a gauge which has the Vernier readings as you would have been exposed to, like when you look at even the Vernier caliper, is a similar type of length dimension readings that you can get. And they're in the order of millimeters. So you apply a mass to the test wire. Before you apply the mass to the test wire, you would have taken note of the reading. Hopefully you would have centered it on the Vernier scale. Now, I just remember that Mr. Hodges reminded me that you wouldn't have had interaction with the Vernier scale necessarily. So with the Vernier scale, here's what it has. It has the scale on it, but it also has, I don't know if you've seen where the construction workers, they work with their levels. And the levels have a tube, and within the tube has a liquid. And the liquid has a bubble, right? And so their aim when they want to determine whether something is level or not is to make sure that the bubble is centered between two lines, right? The Vernier caliper, this Vernier cage also has that sort of liquid with the bubble inside of it, and the whole purpose is to get the bubble to center. Once the bubble is centered, that means that the two wires are considered even, right? They're now equivalent to each other. So what would happen is that you would have the cage put on the two wires, you would center the bubble, take your first reading, right? Then you would attach the mass or attach a weight to it, and that would cause extension of the test wire. Then that would throw the bubble way out, right, out of whack, right? So as a result, you would have to go back now and re-level the cage, making the comparison wire equivalent to the test wire. So what you've done is really extend the comparison wire to match up to the test wire. And then now you will take note of the new reading on the scale. The difference between the new reading and the original old reading on the scale is the amount of extension that was achieved by adding that mass. So then again, having written off the mass and the extension, the amount, the new reading, you would go ahead and add another mass to it. And then that would cause the bubble to go out of whack once again. You would recenter, re-level the cage, and take note of the new reading. The difference between the new reading and the very first reading, the original reading, is the extension. So then you would repeat this for 8 to 9 different masses. So at the end of the day, you would have mass value from which you would be able to calculate the tension force, right? Because you would simply multiply that by the acceleration due to gravity. And for each mass value, you would have a new Vernier reading. The difference between the Vernier reading and the very original Vernier reading is the extension. So therefore, for each mass, you would now have an extension. So once you've gotten the extension, you would now be able to calculate your Young's modulus. So let me go ahead and pull up the screen and we can talk about that. So I'm going to use, for my Young's modulus, what? This went and let's undo that. Oh, I should have cleared the canvas because it looks like I have other things on. All right. So for the Young's modulus, I'm going to use gamma, right, capital. And then I'm also going to use for strain. I'm going to use lambda. Mr. Simpson may have given you a different symbol for strain, right? And then for stress, I'm going to use sigma. So Young's modulus, you should have known by now, is going to be the stress divided by the strain. But Your stress is the force per unit area, which remember I told you is a pressure concept. And your strain is going to be the extension, which is the change in length divided by the original length. So as a result, that means that your Young's modulus is going to be the force per unit area divided by the strain, which will now leave you with is the force times the original length divided by the area divided also by the extension. You can use E for extension, you can use change in length. Please remember, and I've just included it right here, that your change in length is going to be your new length, which is the final length minus the original length. You can use I for initial length, it doesn't really matter, or you can use not to suggest that it's the original. So therefore, you can clearly see that if you want to work out the Young's modulus, you need to know the force value, the original length, the cross-sectional area of the object, as well as the change in length. Now, here's the thing. Each time you add the mass, I just said like you have an elastic band, each time you stretch the elastic band, you see it extending, yes, but it also looks as if it's getting thinner. When you keep adding more and more mass to the wires, they do seem to get thinner. However, you are going to make the assumption that the change in diameter, as a result, the change in cross-sectional area is so small that it is negligible and can be ignored. So you are going to assume that there is no change in the cross-sectional area of the wire as you add masses to it. Okay, so repeating, remember, you're going to make the assumption that there is no change in the cross-sectional area, so the cross-sectional area remains constant even as you add the masses. Now remember, the original length of the wire will not change as you add the masses, right? So remember, generally, if you want to find relationship between variables, you can simply plot a graph of one variable versus the next, right? And based on this equation, where we have that the Young's modulus is equal to the force times the original length divided by the cross-sectional times the change in length, which is the extension, you will notice that the force is changing because you'll be adding masses, that is definitely changing, and the resultant change will be the extension, right? So as you add the mass, the length of the wire changes and causes an extension. The original length will not change because it was there from beginning of time, and unless you exceed the elastic limit of the wire, it will return to the original length once you remove the different masses. The cross-sectional area we said was going to be constant. So as a result, you will notice that in this term, the Young's modulus is a function of everything else, and it will remain the same per material. So you will notice that the only two variables in this equation will be the forces due to the masses that you're adding as well as the resultant extension. So that means that you can determine a relationship between the force and the extension by simply collecting information about force as well as the associated extension and plotting the graph. If there's a proportionality between them, then what you will find is that you will be able to calculate a gradient, which if equated to the other constants in the term will allow you to be able to work out what those other constants are. So that is the wonderful thing about a straight line graph, which is what I said to you in our first class together, is that a straight line graph not only shows you the proportionality, but it even allows you to use that information and calculate some other unknowns. So it shows you the relationship graphically, because an exponential graph does show a relationship graphically too, right? But it doesn't allow you to be able to calculate, whereas the straight line graph, because it is guided by an equation, it allows you to make calculations to get further information. That's the beauty of it. That's why generally, if you want to get more information, your best bet is to go get that to do your straight line graph, or put the information so that you can generate a straight line graph. So for this, here are your options. You want this constant, which is the Young's modulus, and you have two variables. You can either choose to do force is equal to the Young's modulus times the area divided by the original length times the extension. So you can draw a graph of force versus extension, where the gradient will therefore be the Young's modulus times the area divided by the original length. You can then rearrange to make the Young's modulus your subject, because you would have calculated or measured the gradients. And you know the cross-sectional area because you would have, it's going to be given to you in terms of the diameter. And once you know the diameter of the wire, you can get the cross-sectional area. The original length, once measured, you would have that information, and and it is provided to you. So you can either do, and notice there should be no intercepts. Reminding you again that if it is that you're drawing a line of fits, you do not force, even though you know you should have no intercept, don't force it there. Wherever it lands, it lands. Hopefully it lands at 0, 0. But if it does not, you explain why you think it probably didn't. Right? If it does, great. Your next option is, since force is really the independent variable, because it is what you are changing and the extension depends on it. You can instead have drawn the graph of extension on the y-axis, and in that case, that simply means that L naught over gamma A is going to be equal to, times the force. You will have that the gradients will therefore be the original length divided by, in brackets, the Young's modulus times the cross-sectional area. So you can choose whether to draw it of force versus the extension, where the gradient is going to be one way, or you can draw it as the extension versus the force. Some of you may ask, well, can't I draw extension versus strain? Yes, you can. I mean, not extension. You can draw stress versus strain. Yes, you can. In that case, remember that stress is going to, well, let me do it step by step. Just make sure that nobody has any. Remember that Young's modulus is stress over strain. So therefore, that simply means that stress is going to be equal to the Young's modulus versus the strain. And remember, I'm using number for strain. So that means you can draw the stress versus strain where the gradient is going to be the Young's modulus. It doesn't matter which one of these three options you choose. And let me go ahead and circle the three options. It doesn't matter which of these three options you choose to draw your line and your graph. Just remember that your table will be different depending, but you're still going to have to do the same calculations. So for instance, the first two, your table will mostly only have like the mass in kilograms. It would have the force in newtons, and then it would also have the extension in it, right? In the associated units of meters, of course. However, when you're doing the stress first, but then you still have to go further when you do the gradient, you do cross-sectional area calculation and all those different calculations. So you still have to do those, but not necessarily for the table, right? For the stress versus strain, in this case, clearly, you're going to have additional columns in your table, because you can't just draw the graph. You have to present all the data that you use to do the graph, right? And for this one, you needed to calculate the stress and you needed to calculate the strain. So those columns have to be incorporated in the table for the graph, where if you're going to choose to do the graph of stress versus strain, right? At the end of the day, it's the same amount of work irrespective. So it's the same points you'll get. It's just the distribution of the points will be different. Okay, so that is that. You are still going to have errors, I am sure. So as a result, you will have to do the uncertainty in your line of fit, and you will also have to use error propagation to determine the error associated with your calculated Young's modulus. You are not going to do a percentage relative error because you do not know the true value for the Young's modulus for this particular wire, right? If it were presented, then yes, you would have done the percentage relative error. However, please take note that I am telling you that you are going to go on the internet or in your textbook. You are going to find the Young's modulus for different material, and you are going to choose the material whose Young's modulus is closest to the one, the value that you calculated, and you are going to suggest whether you think, or you are going to tell me whether you think the material is made up of that particular, whether you think the test wire is made up of the material for the Young's modulus that you found, or if you think it includes the material for the test wire. If you think the test wire includes that material. So you check your textbook or you check the internet. They will have different Young's models for the different materials out there. You'll see for nylon, you'll see for copper, you'll see for different things. Yes, Mr. Hodges.
Also, Miss, just to ask you, what if you want to, I don't know, what if you want to find the fractional percentage, the error in that, Miss? So delta y over y times 100%.
Yeah, you
No?
can find the fractional error, but the fractional percentage error is still no different from finding the error. It's just an extra step. It's no, so then it's
Okay.
just you quoting it as a percent error
Percentage.
versus an absolute error. It's still the same information,
All right.
right? Because both of them still give you the range within which you think your value lies. And remember, when you look at your graph, it gives you an idea as to how uncertain you are, because if the points are far from the line of fit or they're distributed widely, WILDLY, not WIDLEY, but also the WIDELY, that one too. So wildly and widely, right? If your points are distributed like that, you will find generally, therefore, that means that you're not absolutely sure where your gradient really lies. That means you can't really pinpoint it. That means you have a large uncertainty. And now, at the same time, too, if you realize the points are close, that means you are better able to be precise with it, more sure of where it lies. So that's because, so therefore, you are more, not more accurate, because that's not a matter of wrong or right, but you're more sure of what you think the answer is. Okay, so when you're doing your discussion of your uncertainty, remember, don't just write the uncertainty, because that's what some of you do. You just say there's uncertainty and this is the value, and you leave it at that. If you're going to be telling me what the uncertainty is, you must be in planning to go explain what I should gather from you telling me what it is. So if it is that you're telling me that the uncertainty is this 0.01, and you mean for to tell me that it is huge, then you need to say this is a large uncertainty, but there must be a reason why it is large, because 0.01 compared to 100 is a small uncertainty, but 0.01 compared to 0.05, if the quantity value is 0.05 and the uncertainty is 0.01, it's a large uncertainty based on the quantity. So when you look at the uncertainty, which Mr. Hodges would be better in, because he'll do the percentage error. So he would now see that the percentage error is small and be able to explain that based on this percentage error, we are more sure of I'm more sure of my results. Or if he sees that the percentage error is 60%, then he will say that, clearly, there's some problems in carrying out this exercise or in doing the calculation. And he suggests that maybe it could have been from. If it is that you simply code the absolute error, then you're going to still do the same thing, whereas with percent error is more clear. It's still the same thing, but it's just that you have to now compare to the quantity directly. You have to look at it and say, well, 0.01 compared to 0.05 or 0.01 compared to 1,000, right? So it's still the same work. It's just that whether the work is upfront or on the back end. Okay? So do not just quote it, please. Explain it. And same if you're talking, saying you got your gradient to be X, tell me what that means. Tell me that this fact that you were able to get a gradient means that there is proportionality between. Explain, do not just give me the results. Okay, so that's that. So here is what your data looks like. You notice they're given the mass values and they're given to you in grams. You are at the stage where you do not present that in your report in grams, you present it in kilograms. You'll notice your extension is in the order of millimeters. Millimeters is still a meter concept. However, it's simply using the prefix and giving it in words. You can do the same, but I promise you that if you do, it would be better for you if you use times 10 to the minus 3 and carry it. If you don't, you will forget the 10 to the minus 3 and because remember, you're going to be using this, it means that your Young's modulus that you calculate will be off in the order of, in the 10 to the, by 1,000. So be careful. Make sure that you, even if you use millimeter and use the 2.19, remember when you're doing your calculations to convert it to the 10 times 10 to the minus 3 and put it in your calculator. Here, you also, I remember, so you have your masses, present them, you need the force, you need the extension, you need the title for your table. You also need to remember, this is the diameter that's given to you in row 11. There are 3 different values. The reason is that the diameter for the wire was taken at 3 different points along the wire. So these are the 3 different diameter measurements, which means that you need to average them to get an average diameter. You are also given the length of a notice in millimeters. So then again, if you fail to use the times 10 to the minus 3, your cross-sectional area will be off in the order of 1,000,000, 10 to the 6, right? So please remember to convert your millimeter, to remove the prefix and in your calculations and use the times 10 to the minus 3 instead. This is the original length of the wire in row 12. Note it gives you the uncertainty in the measurement for the length of the wire. You only got one length measurement, so there's no averaging. This is the length of the wire. Remember, for the area, it's considered to be a string, so you are going to assume the cross-sectional area is that of a circle. And so as a result, the area of a circle, for those of you who may have forgotten, is either pi r squared or pi d squared over 4. So you either find the radius from the diameter, so you find the average diameter divided by 2, that will give you the average radius, square that, multiply by pi, and you get the cross-sectional area. Or you use the diameter as is, the average diameter, square that, multiply by pi, and divide by 4. Any of those 2 options is quite acceptable. However, please remember when you're writing your information, define the term on it. If you've defined it before, that's fine. Otherwise, define it just before you use it. Area A is equal to pi r squared. Pi r average in that case, where AR is or means or represents the radius, and then either in brackets or you put the comma, you put the unit associated. Okay, so that's that. Any questions? So that took more than the 15-20 minutes. So let me see. I will give you a little bit of a mental break afterwards, after I figure out who I have here. So we have, yes, Mr. Hodges, I see you. Miss Salmon, she was here. Yes, Miss Salmon, I see you. Miss Morgan Barnes, yes, I see you, Miss Barnes. Mr. Dilly Sterling, I see you as well, Mr. Sterling. Mr. Reggie Scott. I don't see you anymore, Mr. Scott. Oh, yes, I see